Okay, so resuming the lecture, we're going to be doing definite integration as opposed to indefinite integration. There are quite a few different definitions. We're going to do Riemann integration. So this is what we'll be doing. Okay. There in your book they also talk about Darboux integration. So this is in the book. In the past, like the last time I taught this class, which I think was 2 years ago, that was all I taught was the Darboux integration. It's a little bit prettier, but it's less like what you've seen before, so it has that disadvantage. And the set of functions that you can integrate turns out to be exactly the same. Okay. And then, I hope I'm spelling that right, I might not be. There's also, of course, Lebesgue integration. And this would be a more advanced topic. Okay, and the reason Lebesgue integration is more advanced is that you need to know a lot more about kind of the topology of the real number line. By that I mean you need to, we would need to study open and closed sets. We'd need to develop measure theory. And this is actually all in our book that we're going to use next semester. So Lebesgue integration is in that book. I just don't know that we're going to get to it, but there's a chance we'll see it next semester. And Raphael asks, is today the rectangles under the curve day? Yep, that's what it is, but we're going to go through it real quick, okay? Because we just want to get to the actual setup so we can prove some theorems, okay? Any other questions before we go on? So just to be clear, we're doing definite integration with the Riemann definition. Okay. So there's
yeah, does Darboux integration and Lebesgue integration, do those yield the same answers as Riemann integration?
No. Darboux gets the same answer as the Riemann. Lebesgue is strictly better. Okay. All of them will give you the same answers, except that Lebesgue can integrate more functions. Okay. But Darboux can integrate the same set of functions as Riemann. Okay. So yes. Let's do our picture. And this will show us what we need to do. Oops, I didn't really want that line. Here's our x-axis. Here's A to B. Let's draw a function. Let's play around with that. Okay, so here's our function. Okay, so what do we do? How do I get back to my, is that what I want? Yeah. Okay, so what do we want to do to compute the area under the curve? We want to partition our interval from A to B. It's always a closed interval we're integrating over. So at Calc 2 you learned about improper integrals. We're not going to be doing those in this class. The theory works out basically the same. You're just taking the limit. Okay, so we're going to partition our interval into a few pieces. Now, we're going to give these things names. Let me put in a dot 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 here. And then that'll be xn minus 1. And then an xn. So we're going to be breaking our interval into a partition, which is really just a set of points the first one is a, and we call it x naught, and then they're strictly increasing up to xn, which is equal to b. Okay? Now, those are the rectangles we're going to partition this area under the curve into. Now, can you remember back to how you did it in Calc 1? How did you approximate this integral?
Riemann sums?
Yeah, but where did you take the function value from?
On what rule you wanted to use, you could use the left endpoint or the right endpoint, or even sometimes the middle.
Yep. So in the Calc 1 version, you use the left, the right, or the middle, or you can even do trapezoids. Some of you probably might remember you did trapezoids. Okay. In the full theory that we're going to do, you can actually take any point in every subinterval. You can take any point you want. So we're going to call those points the t's. So they're going to be t1, t2, t3, etc. So I'll make them red. Here's t1. Here will be t2. I can take them to be the endpoints. So I can take that to be t3. I could also take it to be t4. Because the endpoints are technically going to be in each of the subintervals. And then I'll have a t5, and then in here somewhere I would have a tn. Okay, that's where we're going to be evaluating the function. So I'm just going to go mark where the function is at all these points. Okay, that's the height of the rectangles, and now we are pretty much good, right? We're going to, let's see if it works this way. We're going to, oops, I went too far. I think I want a different color. Okay, we're going to just form rectangles. Three of the sides are given just by the x's and the x-axis. And then the height is given by these points t. All right, and then we take the area under the curve of each of these rectangles. So really what we're doing is we're summing up. Right, so we picked some t's, I should write that. We picked some t's, and the rule was ti was in the subinterval from xi minus 1 to xi. And now we're going to sum those areas. So the Riemann sum, and this is really a Riemann sum, is going to be the sum of f at the point we picked, that was ti, times the width of the rectangle, that's the difference in the xi's. Okay? That's the picture. And now we're going to get into all the formal definitions. Are there any questions, though, before we do that? Okay, so the big change from Calc 1 is we're being a little bit more less restrictive about where we sample the function. We're allowing ourselves to sample the function anywhere. It's not going to change what functions are integrable. Okay, so keep this picture in mind. Maybe we'll keep it up here as we go through. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I'm now going to proceed to give you 9 definitions in a row. Okay? Because we got to do all of this stuff, okay? So, definitions. Let's have a function. Be defined on the domain a to b, and I mean for a and b to be real numbers. So it's a closed and bounded interval. Okay. Okay. The first thing we did is we chopped this interval into pieces. That's called partition. So a partition of that closed interval, we can actually just define it. It's just a finite set of points where we chopped. Okay, we'll usually use the variable capital P. So what do I mean? It'll be a set of the form in fact, we already wrote this above. Okay. It'll be a set of that form. So the set has a few things that you're probably not used to seeing in sets, right? Okay. So what am I really saying with this notation? I'm trying to say the set has endpoints. Obviously, they're all different. Every element in a set is different. But then if I put them in increasing order, the smallest one is A, the biggest one is B, and then the others are in the middle. Okay? That's all that notation means. There's endpoints in there. Smallest one A, biggest one B. Okay? And please just jump in if you have any questions. That's definition 1 of, what did I say, 9? 9. Okay. Each partition defines a sequence of subintervals, and those have lengths that we're going to give notation to. So each partition determines subintervals which have lengths. Okay, what are the lengths? I'm going to use delta x1 to mean the length of the first one, so that would be x1 minus x naught. And then delta x2 to be the length of the second one, that would be x2 minus x1, and so on. Okay, up to delta xn to be xn minus 1. Okay, those are lengths of a partition, of the subintervals of a partition. Okay, next definition. The longest length of a subinterval is what we call the norm of the partition. So the norm of a partition is the length of its longest subinterval. Okay, I think the picture's going to have to go away now. Just running out of space there. To denote the norm, we're going to put some double bars around P. Okay, now we don't have to do a supremum because all partitions are finite. So they have a finite number of subintervals, so a finite number of lengths, so we just have to do a maximum. Okay, this would be the maximum of the delta x1, delta x2, etc. Or if you don't like using the deltas, just replace them. With the differences. Okay, the idea is as the norm of the partition gets smaller, the accuracy of the Riemann sum gets better. Okay, assuming our function is integrable, we're going to get into that in a minute. Now, what did we do up here? We picked these points T, these TIs, which were where we were going to evaluate the function. Those are like the points where we're sampling the function in order to come up with our approximation for the area under the curve. Okay, we're going to call that, and I'm actually following the book. I'm following most books, I think, here. We're going to call that tagging the partition. Okay, so we're tagging the partition when we add those points Ti, and the rule with those points is that they just had to be in the corresponding subintervals. Okay, so let's go back to our definitions here. So we tag one of these partitions. So I'll write it in. Tag one of those guys by selecting points. Okay, the points we select, we select T1 through Tn, and they're also, well, they don't have to be in strictly increasing order. It's an issue with my notation, but that'll be fine. I was going to call them a set, but let's just make them an n-tuple. Okay, and the rule with these points is that Ti has to be in the subinterval x I minus 1 to xi for all I. Okay, and notice that we're allowing ti to be either endpoint. It can be either on the left or on the right. Okay. Almost halfway through. We'll be halfway through when we're halfway through the next definition here. When we tag a partition, we're going to call that a tagged partition. And this is a partition P. I think we're halfway through now. With tags T. Now, we're going to have to denote, we're going to have to write tagged partitions. We want them to look different than regular partitions. What we're going to do is we're going to put a dot above it. And then if we want to be really formal, when we put a dot above a partition, that means a tagged partition. So it's an ordered pair consisting of a partition and a set of tags, or actually an n-tuple of tags.
Is it like a circle above or like a closed filled in little dot?
It's a little dot. You can look in the book to see how they typeset it. It's typeset just like a period. Okay. Okay, now we have one more silly definition and then three really important ones.
Explain how a tag is an interval again.
The tag is not an interval. The tag has to be in the interval. So the tag is just some point, some x value in that subinterval, and that's where we're going to evaluate the function. Is that okay?
Okay, so what does your notation mean with the parentheses?
When we, oh, here? Yeah, I mean, I wanted to say that a tag, the tagging just, we select a set of points, but I can't say set because two of them might be equal. Because you could take one tag to be the right endpoint, and then you could take the next tag to be the left endpoint, and that would mean that you selected the same point twice.
Okay.
Okay, so I'm just defining the tags to be an n-tuple of points.
Okay.
Okay, so now, what did I say? Oh yeah, I said one more kind of silly definition. We're gonna just extend the notion of a norm to tagged partitions. And it's just gonna be the same as the norm of the partition. So you take a tagged partition, P dot, which is a partition with some tags. It's just the norm. Oops, of the underlying partition. Okay, with the same notation as we defined it above. So let me scroll up just a little bit. There you go. It's just the length of the longest subinterval. Okay. So we've got a partition. We chop the interval a to b into n different pieces. We picked a point from each piece. Those were the tags. And now we want to do the Riemann sum.
How do you find the norm of the untagged partition?
It's the it's right up here. It's the maximum of the widths. Okay, so just find all the widths and take the maximum of it. Okay. So finally, we come to this. The Riemann sum of f. You might not even remember. At the beginning of this definition, we said f is a function from the closed interval ab to the reals. That corresponds to this tagged partition P dot. Is the following. We're going to denote it by S of F semicolon P dot. But it's exactly what you would expect. It's the sum of all these areas of the rectangles. So what would that be? The sum from I equals 1 to n. We take f at our tags, that's where we're sampling our function, and we multiply by the widths. Okay. The book doesn't use these delta x's, so if you look in the book, you'll see the second form. Okay. So the Riemann sum is literally what we did back in that picture. We said we're going to sample our function at some points, and we're going to sum up the areas, and we're going to call it the Riemann sum. Okay. Our idea is that as we partition with more and more points, and the sizes, the lengths of our subintervals get smaller and smaller and smaller, then the Riemann sum should be a better and better and better approximation to the area under the curve. Okay? So we have a name for the longest subinterval. That's the norm of the partition, or it's the norm of the tagged partition. So what we should think is that as the norm of the tagged partitions goes to 0, these Riemann sums should be converging upon some common value. Okay? That is our next definition. It's probably the most important of all of them. So the function f is Riemann integrable if. Okay, now there needs to be. Okay, so I'm going to write, this is going to be written very much like a limit. That's where the intuition is coming from. But you should realize that it's not a limit in the sense that we've studied in this course. So we've studied limits of sequences and limits of functions. This is not quite a limit, but it'll have the feel of a limit. Okay? So I need some value that these Riemann sums are going to converge to. That'll be capital L. So if there is some capital L, which should be a real number, such that, okay, now, again, thinking about the limit intuition, we pick an epsilon and we want to be able to get within epsilon. So such that for every epsilon, every positive epsilon, okay, then there is some delta, okay, and let me emphasize that delta is a function of epsilon, and it's also positive. Okay, now what do we want? We want all the Riemann sums that have norm less than delta to be within epsilon of L. Okay, such that for every tagged partition, P dot of our interval AB that we care about, that have norm at most, that have norm less than delta, what do we want to have? The Riemann sum of F with respect to that tagged partition is within epsilon of capital L. Okay, so let's go through this one more time. There exists a capital L. That's what we need to quote unquote converge to. By converging to it, that means that we're given an epsilon, and we have to be able to guarantee that we get within epsilon of it. Well, guaranteeing we get within epsilon of it means that we can find some delta, so that no matter what tagged partition you take, as long as its norm is less than delta, then your Riemann sum is within epsilon of capital L.
So essentially what we're saying is that for any tag partition, the Riemann sum converges to L as the norm approaches 0.
Mm-hmm.
Okay.
Yep. Yep, that's what we would like to say. I mean, so technically we don't have the notion of convergence for this kind of thing. But yeah.
So we don't have a notion of like a limit of this type of thing, but do we kind of get around that by saying we take a sequence of norms and then we can do limits on that?
Yeah, you can get around it with doing a sequence of tagged partitions. Yep.
Okay.
Mm-hmm. Yeah, so there's a sequential version of this definition that works too. Okay.
Can you give an example of a function that isn't Riemann integrable?
Well, we're going to have examples here in a little bit, but a big class of examples. We're going to prove a theorem that says that if you are Riemann integrable, then you have to be bounded. Okay, so what that means is any unbounded function can't be Riemann integrable. So let's say you define, you look at the function 1 over x from 0 to 1 and just define it to be equal to 1 at the origin. Then that's not Riemann integrable because it's not bounded. Okay.
Okay, thanks.
And when we see the proof, it'll make sense why it's not Riemann integrable. Okay, I promised you 9 definitions. I've only given you 8 so far. So finally, if the above holds, we call L. L is the value that all the Riemann sums are converging to. Well, we don't know that it's unique yet, so let's be careful. We call L A. We call it A Riemann integral of F. Okay, we're being careful here because we haven't established any kind of uniqueness. Okay, now in Calc 1, when you were doing like the Riemann, you were doing the left-hand points and the right-hand points, right? You were actually able to evaluate some integrals. It's a lot harder with this definition. So this definition is gives you a lot more freedom on where you evaluate the function in that subintegral. And therefore, it's a lot harder to actually compute one of these Riemann integrals using the definition. Okay, so we're going to end up proving theorems that basically say, like, look, if your function is nice, then that choice of the tag points doesn't really matter. And you can choose them to make the computation easy. But before we have those theorems, it's really hard to do anything non-trivial. Okay, I mean, we could compute like the Riemann integral of a constant function, which would be exactly what you think, because no matter how you tagged it, you'd end up, right, the f of the ti's would be the same. It would just be whatever the function value is. And then these delta xi's would all add up to b minus a because they partition the interval from a to b. Okay. So yeah, we could integrate a constant function pretty easily. But then you think about even integrating the function x, f of x equals x, and there's a lot of flexibility in how we choose the tagged partitions. So we're going to wait until we have some theorems. Okay. So speaking of theorems, the one theorem I want to prove today will allow us to change this word a to the word the. So I'd like to prove that if you are Riemann integrable, then you have a unique Riemann integral. Okay. So this is our theorem. In the book, this is 7.1.2. And it says, if you have a Riemann integral function, then it has a unique Riemann integral. Okay, so this is kind of just practice with that definition of Riemann integrable. Okay. Any questions before we start proving it? We have.
So
Yep.
when we find this uniqueness, or let me not get ahead of myself, if we can prove this uniqueness, that lets us, for calculating this integral, it lets us choose any tagging that any sort of systematic tagging that we'd like.
Not quite.
Oh, okay. Okay.
So, if we know the function is Riemann integrable,
Mm-hmm.
then we're allowed to choose any tagging we like.
Okay.
Because then any tagging we like will get us to the right answer. The problem is if you don't already know the function is Riemann integrable, then you're not guaranteed that if you take different tags, you might get different answers.
Okay.
So when we say that the function is Riemann integral, are we saying anything about like the norm of the partition in any way? Like, I'm just a bit confused. Like, if you were to have a really large norm versus a small norm, then obviously the value you get would be different, right?
Yeah. So if you look at the definition, we really only care about small norms. Okay. We pick how close we want to get to the right value, or we're told how close we need to get to the right value. We get to pick the largest norm we're willing to consider. We get to pick that delta. And then we have to guarantee that if you have a tag partition with norm less than delta, then you are within epsilon of the right answer of L.
Okay, so we call L the Riemann integral then?
Yeah,
Okay.
and then we call L the Riemann integral. Yeah.
Okay.
Well, after this theorem, we'll call it the Riemann integral once we know it's unique. Okay? Okay. Let us do the proof. This proof should look a lot like uniqueness of limits. It's kind of our standard proof for this kind of thing. We're going to take two potential limits, L1 and L2, and we're going to prove that they're actually the same. So suppose L1, L1 and L2 are both real numbers, and they both satisfy the definition above. Okay. The definition above was said we're given an epsilon, there exists a delta, so that for any tag partition, blah, blah, blah. Let's let our epsilon be arbitrary, because at the end of the proof, we're going to let it go to 0. Okay. And now, from the definition, we were guaranteed, no matter what epsilon we put in, we'd get deltas. Okay, but we actually want, if you think ahead to the proof, we actually want our deltas to be for epsilon over 2. So I'm going to call them, I'm going to use the function version for once. Delta 1 of epsilon over 2. And delta 2 of epsilon over 2. Okay, so that, and again, the definitions guarantee that these deltas exist. The first one says, for every tagged partition, P dot of AB with norm less than that delta. Okay, we have, we're using the fact that L is a Riemann integral. So we want to get with an epsilon, sorry, L1 is a Riemann integral. We want to get with an epsilon over 2 of it. And we're also going to want to get within epsilon over 2 of L2. So I'm going to repeat all this stuff except I'm going to use delta 2 and L2. Okay. Whew. Okay. Now we're gonna do our
I
standard.
have a question about these tag partitions.
Yeah.
Are these the same tag partitions? Like, is in this first thought is p dot the same as in the second one?
No. They're really variables. Right. Because we're saying for every tag partition.
Okay.
P dot, and then for every.
Okay.
Okay. Okay, now a standard trick, we want to take the minimum of the two deltas. So now set delta equal the minimum of delta 1 of epsilon over 2 and delta 2 of epsilon over 2. Let's take any tagged partition of norm less than delta. Sorry, I'm going to have to shrink it again there. Let p dot, now it's a particular tag partition. And just to save me a little bit of writing, let capital S denote its Riemann sum, or the Riemann sum of F with respect to the tagged partition P dot. Okay, now look at what we got. Because the norm of P dot is less than delta, and delta is less than or equal to delta 1 and delta 2, P dot satisfies both of these conditions. So the first one says that S is within epsilon over 2 of L1, and the second one says that S is within epsilon over 2 of L2. Okay, this is exactly the same kind of thing we showed when we showed that limits are unique. Okay, so I realize a minute over, but it's going to take me only one more minute to finish the proof by the triangle inequality. We have standard thing. What's the distance between L1 and L2? Well, that's at most, if we go from L1 to S, plus we go from S to L2. Well, both of those are less than epsilon over 2. So the distance from L1 to L2 is less than epsilon. And this holds for any epsilon. So L1 has to equal L2. Okay, so in our proof we said suppose we have two Riemann integrals, L1 and L2. then we concluded that they're the same, and therefore, if your function does have a Riemann integral, it only has one Riemann integral.
Excuse me?
Mm-hmm.
You accidentally wrote that epsilon over 2 plus epsilon over 2 is less than epsilon.
Oh. I guess that's technically equal to epsilon, isn't it? Yeah. Thank you. Okay, so this stuff won't be on the quiz that we have on Wednesday. The quiz we have on Wednesday is going to be, I believe it was 5-4 up through 6-2. Okay, so no integration Wednesday, and we will resume Friday with more integration. And just to summarize today, all we did was we did the setup for Riemann integrals, and we showed that if you really are Riemann integrable, then you have a unique Riemann integral. We have a lot more to do. We have to prove that, you know, the integral of f plus g is the integral of f plus the integral of g, and other things like that. Okay, so let me stop the lecture there.